There we go. All right. Actually, I have a money making opportunity for you guys. Are we? You guys like money? Okay. All right. So here's the deal. It is all technically legal, and while you're going to start small, I'm going to start you at $15 an hour. I can guarantee that after 1 year, you will be making $1 million. Okay. So you start small. You got to work your way up, right? Right. So you're going to start at $15 an hour, but I can guarantee you that at 1 year, you're going to be making $1 million. Who's in? Who's in for this money making opportunity? One, two, three, four, five. Hey, everybody. Hey, let me. This is the most important lesson I'm ever going to teach you guys. Don't sign on until you have all the information. I should probably describe this to you in greater detail. So here's your dollars per hour, and here's time going by, and here's right now. You guys don't have to write this down. You can just watch me for a second. And here's year one. How much did I guarantee I would start you guys at? Okay, so we're going to start right here at $15 per hour. What did I promise you at year one? $1 million. Okay, so let's imagine this is not quite going to be to scale, but let's imagine that we got $1 million per hour right there. Here's the graph of your earnings over time. Limits and values are not the same thing. This would be a great example of where the limit is not equal to the value. Let's talk about that for just a second here. If I asked you for the value of your earnings at year one, what would you guys say is the value right there? That means when you plug in one, what do you get out of this function? Okay. But if I asked you for the limit as time approaches one of this function, that means what is happening as we get really, 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 really close to one, but not what happens at one, right? So, what would be the limit as we are getting really close to one? Yeah. And you can see that you are earning $1 million for only a fraction of a moment. Okay, so the moral of today's lesson is that there is a difference between limits and values. And let's see if we can use that to draw some graphs. Okay, let's take a look at this one right here. The important number on this one is 2. We are interested in 2. I'm going to mark 2 right there. Boop. I'm actually going to start over here. Can you guys see that this is telling you the value of the function at 2? So if we were going to draw a graph for that one, and that's the goal here, you're going to draw a graph if it's possible. And if it's not, you're going to write, I don't think so, Klein. We would have to say 1, 2, 3, 4, 5 right there. That's the value. Now, this right here says that the limit as we get close to 2 is 4. So what I would want to see from you guys is something like this. Here's 4. If I come over here to the left, boom, 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 you can make it do whatever you want. It can go, woo, 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 it can bounce all over the place. But as we're getting close to 2, this thing has to be getting really close to 4. Now, why am I putting an open dot right here at 2 rather than a closed dot? Yeah.
Because there's a hole in the function. It's not actually there at that point.
I agree with that. And also, let's suppose I did put a closed dot right there. What would that do? Why would we be in huge trouble then? Yeah.
Make it not a function because there's 2 values that we want.
Yeah, yeah. right? We would have two outputs for that one input, which is insane, right? That would be like putting bread into the toaster and then like toast comes out, but so does spaghetti. Like that can't happen. So, all right. So this side has to go right there. Now, what about the other side? Technically, the other side also has to be creeping in on 4. And if I can do a little zoom in here, I want to remind you guys that this right here is the left side. Do you remember the way that we notate the left? We say the limit as x is approaching 2. Then there's a little mark that you put in the exponent to show off that it's the left. What is that? You guys can just call it out. Yep, little minus sign. So the limit from the left side of this guy has to be 4. And then over here, so that's this right here. And then on the other side, as we're creeping in from the right, the limit as x approaches 2 from the right side is the plus sign. Also has to be 4. If it tells you there's a limit in general, that means that right and that left side, they have to be going to the same place. You guys cool with that? Boom, 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 boom. Let's do one more. Let's do the next one. All right. So interpret this. This says the limit from the left is 4. Okay, so I can handle that. I can say, here's 2. Ba-doom. Here's 4. Ba-doom. Ba-ba-ba-ba-ba-ba-ba-ba-ba-ba-ba-ba. There we go. On the left, approaching 4. This right here says the limit from the right is 5. Okay, I can handle that. Here's 5. Come up to 5. Beep, 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 beep. Right side's going to 5. Now, if the left side is going to 4 and the right side is going to 5, these two different sides are going to different places, then we have to say that the limit in general at 2 doesn't exist. Because this side and this side are going to different spots. There's no one number that is getting close to. Does the limit does not exist mean something special? Is it from, what's that movie? From Mean Girls? All right. So we would say in this case, the limit as x approaches 2 of the function does not exist. Okay. And once again, the reason for that is because 4 is not 5. It's true. Think about it. Okay. One last thing. Look here. This says f of 2 is equal to 5. That's telling us where to shade at 2. So I'm going to come up here and I'm going to shade the top one because of that. You guys good on number 2? All right, here's what I'm going to do. I'm going to be quiet for a little bit. I would like you to either on your own or with a partner work through the rest of this page right here. And then when you're done with that, I want you to flip over and I want you to try this second page. Once you've attempted all of this and all of this, you are good. Okay? Questions? All right, go for it, gang. Hit the record button and away we go. Number 3, I don't think so, Klein. Number 4 should look something like this, and number 5 should go through this point, and it should have a slope of 1/2. Okay. So I just went through 3 answers there. Which ones do you guys have questions on? What do you want to talk about?
So what's the rule of like having like a point on an asymptote?
You can do it.
Yeah. It's just like a hole in the asymptote.
It would have to be defined something like this. It would be like f of x is defined such that when x is not 2, it's 1 over x minus 2. And when x is 2, it's 5. So you would have to define it in some unusual piecewise way to get that point there. But was that? Yeah, you got to pick a wheeze it. All right, anything else on this page? Okay, let's flip the page then. We're going to go one line at a time. First line should go 2, 1, D, and E. If you got that, give yourself a little pat on the back. Any we want to talk about right there? 1, 2, or 3? Okay, let's go then. The next line goes 1, 1, 1. We good? We good up to there? All right. Third line goes 2, 1, 2. 2, 1, 2. How we doing? Questions up to there? You guys are too good. Okay, the next line goes infinity, negative infinity, undefined.
Or they cheated. They put 8 instead of 9.
What was that?
I did it. Oh, we did it for 8.
Oh, I didn't. Sorry, I didn't tell you there was a typo.
That's fine.
So if you did it for 8, you probably said it was 1.
Yeah.
Yeah. So we're good with those? Good with those 3? Okay, last 3. The limit as we approach infinity is 0. The limit as we approach negative infinity is 1. Okay, we want to talk about those two?
Um,
So
what was the first one?
just the first one? All right. So x going to infinity means we're over here on the right. So on the right, as I'm tiptoeing this way, what's happening to the y value? It's increasing, and it's approaching a particular number.
But how do you? I mean, how do you know it's approaching? Because I mean, it could. It'd be like a logarithm and go past it.
I suppose it could. I was trying to express, since it didn't pass it, that it's getting close to 0. But I see where you're coming from there. Okay. On the other side, this thing is kind of bobbing up and down, but you can see that it's slowly like getting closer and closer to 1. All right. The last one is the tricky one right here. The limit as x goes to infinity of the derivative. Any brave souls want to throw out a guess on this one?
It's a 0. Nothing's wrong.
Shoot. What did you say it was?
Oh, 0.
It is 0.
Really?
Yeah.
Oh, wow.
Okay. Now here's why. We're looking when we're talking about the derivative, we're talking about the slopes, right? Throw me a right.
Yeah. Right.
Okay. So slope is positive. Moving over closer to infinity. Slope is less positive. Scooching over even further right here. Slope is really shallow, isn't it? Can you see that those slopes are leveling off to 0? Okay, and that's why the last one is going to be 0. Okay, you guys good with that? All right, here's what we're going to do. I'm going to stop the lesson right there for now, hoping the seniors will be back in like 10 minutes. And then there's one more piece that we're going to do. Okay? Let me hit the stop button. And I am hitting record again. Here we are on September 14th, National Coloring Day. And we're going to look at this guy. So now we're going to talk more about limits, but I want to use functions this time. So this guy right here. Here's what I'd like you to do. I want you to turn to a neighbor, say, hey, neighbor. And I want you to make a guess with your neighbor what this function looks like. If we graphed it, what would we see on the graph? Go for it.
There would be an asymptote at
Or hold on.
yeah.
could fax it, figure it out. There's no value.
Which is wedge.
And then, what was it again when this is the higher, this is the higher degree of my law? So, I think that means you have to do.
Hey, and I'm just looking for some ideas here. Any guesses about what this graph is going to look like? Guess.
So I remember when it comes to like the one of the ones where it looks like that, I don't remember if it's a numerator or denominator, but one of them are the asymptotes and then the other are the x-intercepts.
Okay. So there could be an asymptote. If there was an asymptote, where would that asymptote occur? What x value? At x equals 3? So do you guys buy that that's a possibility? Asymptote at 3? I definitely agree that 3 makes the denominator 0. So this thing's not going to be defined at 3, right? We know that 100% for sure, guaranteed, not defined at 3. Okay. Is that the only option? Asymptote at 3. Cameron's got another idea. What was that? There could be a hole at 3. Okay, that would be another way that it would not be defined at 3. So let's start by figuring it out this way. Let's just test a few values. Let's plug 0 in. If I plug 0 into this function, no calculator here, just look at it. Those go away. What are we left with? -3 over -3, which gives us 1. Okay, so we know it's going to go through that point right there. Next one, let's plug 1 into the function. So 1 minus 2 minus 3 is -4 over 1 minus 3 is -2. -4 over -2? Okay. So it goes through that point. Let's plug 2 in. So that would be 2 squared minus 2 times 2. Those are going to cancel out, aren't they? So we get -3 over 2 minus 3 would be -1. That's going to give us... Oh, okay. I see a pattern going on. Do you? 1, 2, 3. It is linear. So bump, 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 bump. Now, if I plug 3 into this function, look what happens. The denominator would be 0, and the numerator would be 9 minus 6 minus 3, which is 0. So we're getting 0 over 0. Uh-oh, right? That's not defined. So at 3, we have to put a hole. Okay, and then it's going to continue as a line after that. If I asked you for the equation of that line, like y equals, what's the slope of that line?
1.
Slope of 1, and the y-intercept is 1. So we could say the equation is y equals x plus 1 with a hole in it. Okay. Now that was a lot of like hunting and pecking and plugging numbers in. Is there a way that we could have figured out it was going to look like this by playing around with the numerator here? Yeah. So you factored this right here. And x minus 3 like that. You guys see that? And so the x minus 3s are going to cancel. And notice that what happens when you do that is you actually get a piecewise function. You get that this thing is equal to x plus 1 anytime x is not 3. And that it is undefined when x is 3 because of the zeros. You with me up to there?
Where did you get the x plus 1 from? Oh,
When you cancel those, there's the x plus 1. And look how neatly that works out. Isn't that what you guys told me the slope was right here? Y equals x plus 1. Okay, so it all kind of fits together. The moral of the story here is that while the value would be that f of 3 is undefined, the limit would be that the limit as x approaches 3 of f of x is, well, there's two ways that you can get it. One is you can look at the graph. If you look at the graph right here, as we come in from the left and the right, what y value are we getting really close to over here? Okay. So since this and this are both approaching 4, we could say that the limit is 4. There's another way you can get it, and I actually think this one's easier because you don't need any picture at all. Look what happens once we've canceled the x minus 3's. See how we're left with the x plus 1? You can just plug the 3 in there. 3 plus 1 gives you 4. So the game for like the next 15 minutes or so is going to be, rather than looking at a graph, we're going to use the algebra to find our limit. Okay? One last thing I would like you guys to write down. I want to make sure that you understand the difference between these two things. The value is what happens at x equals c. I'm going to underline the at because that's the important. What happens at that point. Whereas the limit is what happens near x equals c, but not at. All right. So with that in mind, I want you guys to flip the page. We're going to do 4 examples so you can kind of see the different ways that we can use algebra to find limits. Ooh, coffee is good. All right. I'm going to ask you a question. The answer is 1. What's the limiting value?
1.
Very good. Very good, gang. So that number right there is your limiting value. If you plug that number into the function and you get a number out, you're done. That means that the limit and the value are the exact same thing. So you always want to start by plugging that number in. And in fact, in this case, look what you would get. You get 2 times 1 squared minus 7 times 1 minus 4 in the numerator, and 1 minus 4 in the denominator. Let's see, what would that be in the numerator?
-9.
-9 and a -3. And so that would give us 3. Okay, so that tells you a couple things. That tells you that your limit is 3. It also tells you that on this particular function, at 1, this thing is continuous. It's just rolling right through where 3 is. The limit and the value are the same thing. So there's the first example. Now, second example. I'm using the exact same function again. This time, what's our limiting value?
4.
We got 4 right here. So let's see what happens when we plug 4 into this bad boy. 4 would make the denominator 4 minus 4. The numerator 2 times 4 squared minus 7 times 4 minus 4. So 0 over 0. Yeah. Okay. When you get 0 over 0, this has a name. It's called an indeterminate form. Think about indeterminate. If something is indeterminate, it means it can't be determined the way that it's written. This is telling you that you need to factor this function and then go at it again. Okay? So we would look at the numerator and we would say, all right, how can I factor this guy? And this is actually easier than regular trinomial factoring because you already know what one of those factors is going to be. Guaranteed. Yeah. Since 4 makes this 0, you know there's going to be an x minus 4 right here, which means that for the other one, you barely even have to think about it. You just got to say, what times 2x squared would give me x? And then what times -4 would give me -4? This is where you guys say 1. So there's the factored form of the numerator. Let's look at what this does. This means that the limit of the function of this function is the same as the limit of 2x plus 1. I canceled the x minus 4s away. We're left with this. Once you get here, you plug your limiting value in again. And you'll notice that this time you get 2 times 4 plus 1, which is 9. So 9 is our answer. 9 is our limit. If you were to be looking at the graph, you would see something that looked like this. Bum, 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 bum. Here's 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's 9. It would look something like that. Okay, gang? Hey, seniors coming in. I just hit the record button, so it's recording the lesson for you guys. You'll be able to watch it later. Yep, no problem. All right, so we got the first one. We got the second one. Let's go to the third one. Okay. Now you'll notice that on this one, I only changed one single thing. I switched the minus 4 to a plus 3. Okay, so when I plug the limiting value in right here, aren't we still going to get 0 in the denominator?
Yes.
But this time we're going to get a different number in the numerator. Let's see, what would that be? That would be 2 times 4 squared minus 7 times 4 plus 3. So we got a 32. Take away a 28. That's 4 plus what? That is 7 over 0. This one is not an indeterminate form. In this case, we know what happens. If you have a number divided by 0, it is asymptote time. What this tells you is that rather than having a whole, this one at 4 is going to have an asymptote. Now, I don't know whether it's going to positive infinity, or it's going to negative infinity, or it's going to two different directions. Could be any of those, right? So when you see this situation, a number divided by 0, you're going to say that the answer does not exist. There's no limit there. So that's the third case. Molly.
I'm kind of jumping in here. I don't know
Yeah.
how to feel it, but could you not write the limit like from the left side and from the right side, or are we just not?
You could. It would get kind of complicated with this one. We're looking at how we can do this without a calculator.
Okay.
You know, if you had a calculator, you could definitely graph it and look at it,
Right.
or you could test numbers that are a little smaller or a little bigger. But because we don't have a calculator, we just know that when we get 0 over 0 like this, it means there's going to be a hole in the graph, and factoring will find us the limit. Whereas when we get a number divided by 0, all we can say is that the limit doesn't exist. Okay? So let's go. Yeah, Jonah.
If they were to both go in the same direction, what would the effect?
Good news. If they were both going in the same direction, like they're both going up, I think it's acceptable for you to say the limit is infinity. And it's also acceptable for you to say the limit does not exist, because infinity, not a number. Okay? So I would say, as a cover all your bases kind of situation, anytime you get this result, when you plug in the limiting value, you can definitely say that the limit does not exist. Good question. Okay, anything else about that one? All right, this is the last one. Check out this guy right here. X cubed plus x squared minus 2x minus 8 over x minus 2. And we are plugging in 2. We want the limit at 2. So let's start by testing what happens when we put a 2 in. So 2 minus 2 down low. 2 cubed plus 2 squared minus 2 times 2 minus 8 up top. I know I'm getting 0 in the denominator. What about the numerator? Is that also 0? I got a confirmation on that? 0? Okay. So let's see what we've learned. When you see 0 over 0, what do you have to do with the numerator? You do. Okay, now let's talk about ways that we can factor that. One way that you can factor it is by dividing. So since this is a degree 3 and those are kind of hard to factor, I would divide this by x minus 2. Now, how do you guys feel about synthetic division? I gotta love it. I gotta hate it.
Why can't we just do
Anyone saying it's mid?
It's mid.
Mid.
Why can't we do
It's
exactly
very
like group
mid.
it?
Very.
Because you can't take out, you don't get 4.
It won't work. This particular one will not work by grouping. You could try. Sometimes it'll work. I picked this one out specifically so that you have no avenue but to divide. Because I wanted to go over dividing with you guys. All right. So let's do a quick synthetic division here. I'm going to write the synthetic division over here. We're dividing by x minus 2. So a 2, the root, goes right here. In the numerator, we've got a 1 and a 1 and a negative 2 and a negative 8. Do you remember what we do with the 1?
Break it down.
Bring it down. 2 times 1 is
2.
2. Add them together.
3.
Yeah. 2 times 3 is. Now we're rolling. Negative 2 plus 6 is. 2 times 4 is. Ooh, and the endorphins. They are firing. We are feeling good because look at that right there. The remainder.
Love that zero remainder.
Doesn't that? Don't you get that like? Oh, yeah. What a relief when that 0 appears.
Maybe that's why you're the math teacher.
Perhaps yes. I do this for my mental health. All right. So what does that do for us? Well, let me answer that question. That tells us that x minus 2 is a factor of the numerator. Going to get an x minus 2 right here. And that when we divide an x minus 2 into the numerator, the remainder is this right here. Do you guys know what the 1, the 3, and the 4 are telling us? X squared. 1x squared plus 3x plus 4. These right here are giving us ba-boom, ba-boom, and ba-boom. So, home stretch. What are we going to do? We're going to take this and rewrite it as the limit as x approaches 2 of, say goodbye to the x minus 2s. They are going to cancel away. X squared plus 3x plus 4. Take that 2, plug it into the quadratic that we've got now, and we get 2 squared plus 3 times 2 plus 4, which is 14. That's your answer. For 4,000 extra credit points, if we were to look at the graph of this bad boy right here, what would it look like? It would look like a graph. I'll give you half the extra credit points for that. So there's still 2,000 of them on the table. Give me some details about this graph, Jonah. Okay, so at 2, right here, there would be no value. This would be a 14. I'll give you half of what's left. So you got 1,000. Give me a little more detail. What's going on around it? Yes, Eli?
It'd be a parabola.
It would be a parabola. How did you know it was a parabola?
Because it's x squared plus 3x plus 4, which is a trinomial, which is gives you a parabola shape.
You got it. Okay, so parabola tells us we're looking at that.
Can I get like 500 for that?
No, I'll give you the rest. I think we're good.
Yeah, we had 1,000.
Yeah.
2,000.
Mm-hmm.
No, because
No, we had Matt got 2,000.
1,000.
Jonah got half of that.
That is good. Okay, so
I don't want to continue this process of halving because eventually I'm going to be like, you get 0.125 of an extra credit point.
Well, so I get 1,000 out of 35. I'm at the front. Thank you. So
All right, so let's see. Where are we? in summation, today's lesson boils down to this. You trying to find a limit, right? I want to make sure I put here. If you plug in the limiting value, right? Like the limiting value was 2 here, right? Give me a right.
Right.
If you plug in that 2 and you immediately get a number, then good luck. Happy day. You're done. The limit and the value are going to be the same. They're equal to each other. That's the easiest situation. If you plug in the number like the 2 and you get a number divided by 0, congratulations, you're also done. That's the situation where the limit does not exist. So number, it's the number. Number over 0 does not exist. Finally, if you get 0 over 0, to be clear, that's not a percent sign. 0 divided by 0. Uh-oh, it's an indeterminate form. Now you've got to go simplify that thing, right? Factor it, simplify, and then figure out what your limit is by plugging in the limiting value one more time. Klein out.
Woo.